All right, so welcome back. So let's do 832. So let's look at partial derivatives for again functions of on the Euclidean space Rn. So this is another way of generalizing the derivative from one variable, right? So we have either the total differentiability, right? The derivative is linear operator, but there's another way, which is that we take partial derivatives, right? What our partial derivatives is, well, instead of trying to generalize the definition, we instead say, well, let's just try to manufacture functions of one variable and differentiate those. So what we're going to do is basically you move in just one direction and you differentiate in that direction. So at first we're going to just move in one of the directions of one of the coordinates, right? Let's say the jth coordinate. So we look at what happens when we shift the jth coordinate by h, right? Where now h is no longer something in Rn. Now it's just a real number, right? It's a small non-zero real number. It's supposed to be non-zero, otherwise you're dividing by 0, right? But we're taking a limit as h goes to 0, right? So that's what we're looking at, right? I mean, we look at the difference quotient as we moved in the jth direction, right? An easier way of writing it, this is maybe a little messy, right? We take x and we add h times the jth standard basis vector, right? The 1 0 0 0 0 0 0 0 1 0 0 0, where the 1 is in the jth spot, right? The standard basis vector for the jth coordinate. All right, so that's the definition, if it exists, right? That's what we call the jth partial derivative of a function. So now we're just talking about a real valued function, right? Now, if we have a mapping into Rm, right, from Rn to Rm, right, that means that there are m components, right? So we can write this f, right, this f as m functions into R, right? So m functions like this, right? So then you just take partial derivatives of those guys, right? So for each k and j, you have a partial derivative, right? So you have m times k guys that you can compute. If you can compute them, right? You can try to compute, right, at every point, right? So there's n times k numbers, right, at each point that you can compute. All right. Well, let's look at sort of pictorially. Let's look at what happens. So let's suppose that let's look at the graph of f, right? And let's just suppose that m is 1, right? So it's a function. It's just a function into the real numbers, and we have we're in R2, right? So it's a function from x1, x2 into y, right? So from R2 to R, right? And here I've drawn the graph of it, right? So the graph would be in 3 dimensions, right? And it's this surface over here, right? That's giving you the values of f over points in the x-plane, right? Now, what is the partial derivative, right? So the partial derivative with respect to x2, right, means that I look over here and I'm gonna move back and forth in the x2 direction. That means moving on the graph like this, right? just along this little this curved bold line, right? So as h moves, you move in that, right? So you're taking f of right. You're looking at f of x1, x2 plus h, right? You're looking at this thing, right? And you're subtracting the f of x1, x2, and then dividing by h, right? That's the difference quotient that we're looking at, right? And so, what is it that we get when we take a look at this difference quotient? Is basically I'm just ignoring x1. I'm just thinking of it as a function of x2 and taking the derivative. So the derivative is the slope of the tangent line to this graph, right? So you can over here what I've done. So let me go erase all of this. So what I've done is basically I've drawn if I look at the x2y plane, right? Everything is just in this plane, right? You think of a plane that cuts the surface, right? So it cuts. You just get this this line that's your graph, right, in that plane, and you differentiate, so you get the slope of this line inside this x2y plane, right? That's what the partial derivatives is, right? That's the geometric interpretation of the partial derivatives. All right. So, let's zoom in a little bit. All right. So now, if you noticed, so here it's, I guess, n and m. If we have a function from Rn to Rm, we had the m by n possible numbers, possible derivatives that we could compute, right? We can put them in a matrix, right, like this. Let's put it's always the first function, second function, and all the way up to the mth function, right? In the mapping, right? The components of the mapping, those are the rows, and the variables are the columns. So x1, x2, all the way up to xn, right? So the columns are the variables. So that's how we're going to organize it. Now, the thing to notice is that this is a matrix that has the right dimensions to be a derivative, right? And so the proposition is that suppose that I have a differentiable function at some point, then the partial derivatives actually exist at that point. All these partial derivatives, all the ones for this matrix, in terms of the standard basis. So we're just like we just did, right? And the derivative is represented by this matrix, right? It is this matrix, right? So oops, right? So let me get rid of all of those, right? In other words, how do you represent a linear operator? You can just say, what does it do on a basis, right? So it takes the jth basis element to this vector, right? So the coefficients are given by its partial derivatives, right? So this is just writing it for a general vector, right? If I write the vector in terms of the standard basis, right? So it's this vector over here, right? That's what v is. This is the derivative applied to v, right? That gives you precisely what what it is in terms of as a mapping, right? That gives you a formula for what it is. All right, so let's prove it, right? So let's fix J, right? fixed sum j, and we're assuming differentiability, right? Now, so let's look at the thing that we'd want to go to 0, right? So let's look at the norm of this guy. We'll see that that's what we want to go to 0. So this is the difference quotient. We wanted to go to something, and I claim that this is the thing that we wanted to go to, right? So notice this is still, these are vectors in or at least the top here, right? This is a vector in R M, right? This is also a vector in Rm, right? This is an m by n matrix. This is a vector in Rn, and so this is a vector in Rm. Hopefully I'm getting all of these letters correct, right? Now H here, right? We're doing partial derivatives. That's just a number, right? So that's I can definitely do that. I can definitely write that down. That's really just multiplying this vector by 1 over h, right? So I do this. I put it over a common denominator. I get this thing here. Now that sort of looks like the thing that I'm getting with differentiability, right? There is the derivative, which I know exists, times times a vector. Then that's the vector that I'm adding, right? That's the originally that was h, right? But now it's h times ej. It's still little displacement, right? So I'm applying that to the vector. It's not quite the right thing. I have in the denominator over here, I have h. I want the norm of the displacement, but if the displacement is h ej, the norm of that is h. So right, I have that, right? So this, I know that this goes to 0 as h goes to 0 because f is differentiable, right? So that's good. That means that the limit of this in Rm, right? This is a quantity in Rm, if you remember. The limit of that is what we just computed it using the definition, right? So okay. Right, so let's represent, again, just like before, f, by its components, right? And taking a limit in Rm is the same as taking the limit of each of the components, right? Something that we proved last semester, right? So it's the limit in the Euclidean metric, right, is the same as the limit in taking each component separately, right? So for every k, right, so k is something from 1 to m, we get that this limit exists, right? Because we know that the limit existed when this was f, not fk, but now we know that it's actually, we can just take the components, right? So that means that this thing exists, and well, that's the partial derivative, right? By definition, right? The partial derivative is precisely this limit if it exists, right? Now we know that it does exist, so that's what it is. Now we've just proved that the limit of f, the limit of the difference quotient was f, not fk, was this guy over here. So this is the kth component of that, right? So the kth component of f prime of p applied to ej is this guy. Well, that's, we're done, right? Because this, if we think of it as a matrix, again, everything's standard basis and all that. This is the jth column, right, of that matrix. The kth component is, so it's the kth component of the kth entry in the jth column, right? So it's the entry in the matrix. Let's go back to the proposition, right? For example, if it was this is when k was 2, right? It's the second component in the nth column, right? Right. So, by the way, the converse of this proposition is not true. Just because you have that the partial derivatives exist does not mean that the function is differentiable. So that's that's a little bit of a bummer, right? Because the partial derivatives, we have lots of calculus, right? We can compute it in many ways, right? But just because you can compute the partial derivatives doesn't necessarily mean that you have the derivative, right? The partial derivatives do not imply a derivative. The other way around, yes. And if it's differentiable, then the partial derivatives give you a way to compute the derivative, right? But it first has to be differentiable. Now we will prove, later that if the partial derivatives exist everywhere and are continuous, then the derivative exists. That's not quite, that's not quite the right sort of, if and only if. That's sort of a sufficient condition, but not a necessary condition for differentiability. But at least it does, it will give us a way of, showing that something is differentiable in terms of computing the partial derivatives, which are easy in terms of all this calculus that we know. So let's essentially, end it here. By the way, maybe I did, I should say this is one of the consequences of the thing that we just proved. We will be interested in things that have a continuous derivative. Now, the derivative, right, is a function from the domain into the set of linear operators from Rn to Rm if it's a function from Rn to Rm. And this proposition says that suppose that it is differentiable at every point, right? So that we get this. So once you have differentiability, that the derivative is a continuous function, if and only if the partial derivatives are a continuous function, right? So seeing the continuity of the derivative in either setting is just right. I mean, either this thing is continuous or all of these are continuous, right? So that's also what we've, that's a consequence of what we've proved, right? But we'll actually show that if these guys exist and are continuous, then this thing exists. And it's continuous, right? Now, it doesn't really help if it's not continuous, but functions with not continuous derivatives are, somewhat ugly. They exist, we have to deal with them, but yeah. All right, so let's end it here, and we'll again, we'll do this. We'll do 833 as another lecture. So let me turn this off.